it's a little bit more complicated. If your shard key isn't unique enough, like for instance, if we made a shard key on application, Mongo isn't going to be able to distribute that very well. So let's say half of our documents are Nginx and half of them are some other application. There's only going to be 2 chunks in our database because the cardinality is 2 on that shard key. And Mongo's not going to have much ability to balance that and move those around and split them up. We want something with a little bit more cardinality than that. Like for instance with email, everybody's going to have a unique email address, and so it can split it up as it needs to. And if there's 1,000 L's, it can split those up as it needs to. But then there's also a problem if you make your shard key on a timestamp. The problem with that, it's very unique. Everything within 1 second is everything outside of 1 second is unique. But the problem with that is all of your data is going to be being written to the same place because timestamp. Everybody has the same timestamp as all your data is coming in. So if it's writing to right now, everything for right now is always going to be writing to this one place. And so you're going to have a hotspot in your database for writes because everything is always writing to the same place. In this case, probably the best option would be to actually just create a field. I would do maybe an MD5 of the app and timestamp together, which gives you a unique string that's constantly changing, gives you high cardinality, and gives MongoDB the ability to split things up as it needs to. But you can also compute it ahead of time. So at query time, you can know what this MD5 is. So you can query for this MD5, which you compute at query time, which is the combination of these two, and Mongo will know how to fetch it. Okay, as I was explaining that, I realized I probably should have gone into this first. So sharding, the way sharding works is it will split your collections into chunks. And a chunk is based on the shard key. So when you first create a collection, there's one chunk in your shard, and you insert a document and it goes into that chunk. Let's say it's on username, and that chunk is going to have a range from A to Z. That's your one chunk. As you start adding a bunch of users, let's say you get 1,000 users. Probably at some point, Mongo is going to want to split that into 2 chunks, and a chunk split happens. And then, depending on your distribution of users, it may split A through F into one chunk, and G through Z into another chunk. And now you've got 2 equal-sized chunks, assuming that you've got more A through F users. And Mongo can then do what it needs. Now as you get more users, let's say you get 1,000 L users signing up. Now Mongo might split that other chunk. Now you've got 3, and it can move these around. So this is an end result of what it might look like: A through F, M through F through M, and all this. So you might have, if you had 4 chunks. And the way Mongo splits them is based on size. So if it's 64 megabytes or 100,000 documents, it will create a chunk split event and split that large chunk into 2 32 megabyte chunks and then move them where it needs to. And I already talked about all this. Actually, if it's time-based, you'll always insert into the same chunk. So let me talk about that. So if this was timestamp, for instance, the reason that could become a problem if timestamp was your shard key was because when you're writing, everything is going to always be writing to this last chunk because timestamp is always moving forward, and it's going to split somewhere in behind the current time. It's going to be splitting old chunks off, but you're always writing to the most recent chunk. So that can be a problem. Okay, so moving on to that other section over here in that diagram, the config servers. As I mentioned, there could be 1 or 3 of them, and they handle data a little different than Mongo itself handles data. They're very conservative with how it accepts and confirms that data has been acquired and saved. So if something is saved into the config server, you can assume that it's saved, which you can't necessarily always do in MongoDB itself. And it does that with the 2-phase commit. So kind of an acknowledgement and a double acknowledgement there. If any of the 3 config servers are down, the metadata goes read-only. So at that point, chunks can't move around, it can't do any chunk splits, but you can still access your data because it still knows where the data lives. You can still query, and you can still actually write data to your database. It's just that if you're in this state for a long time, your chunks might get imbalanced because there's no splitting going on. So you want to get your config servers up and going as quickly as possible. So a cluster can be online as long as it has 1 config server up and running, but no splits or migrations will happen unless all 3 of them are up, so that it knows that it has good, solid, consistent data. And the reason this is so important is because, remember, this is the only way that the MongoDB process knows where your data lives. So if there's corruption in the config servers, it's going to have no idea where your data lives, and it's essentially useless to you at that point. You can't query it. So it's very important. That's why there's these kind of restrictions on here, config servers. I actually already talked about all of these. The MongoDB acts as the router. You connect to it just like you would a MongoDB if you're an application. One interesting aspect of this is it's actually very lightweight. It's surprisingly lightweight. You would expect it to be pretty heavy, being that it's a centerpiece of Mongo. But you can actually run it on all of your app servers. So if you have 10 web servers serving up your application, a smart way to do it would be to have a MongoDB running on each one of those, so that it's less network communication you have going on, and it's not one point of failure. So if you have 10 of those, one of them goes down, maybe 1/10 of your people that were using that web server might not be able to access it, but everybody else would still be up. So you can have as many of them as you want, and they communicate with each other to make sure that they're all in sync. So the way writes work in a sharded environment is, I'm going to talk about 2 concepts in the next 2 slides called routed versus scattered reads and writes. A routed read or write means that it goes directly to the shard that it needs to, and it can figure that out because it knows the shard key if you add that into your query. A scattered read or write would be if you do a query or a write on something that's not the shard key, in which case it could live on any of your shards and it doesn't know, so it has to basically broadcast to all of them and say, well, let's say in that other example, my zip code, that's not a shard key. So if I wanted to query everybody in my zip code, 27540, it would have to issue those out to all of my shards. Each of the shards would return everybody that has 27540 as a zip code, and the MongoDB process then would group those together and send them back. So that's called a scattered read or write. So that's the difference between routed and scattered. So inserts, for an insert, you can only do a routed insert, and that makes sense because you can only write it to one place. So you have to know the shard that it's going to go to. So when you write data, when you insert it, you have to have the shard key as part of it. So if you're creating a user and your shard key is username, you have to include username in the user, which makes sense. I mean, you wouldn't do it otherwise. For removes, if you're deleting data, you could do both scattered or routed. It doesn't matter. You could say delete everybody in the zip code 27540, and that makes sense. It would send that out to all the shards. All the shards would do their own little bit of work and return. The same with updates. You could update, give everybody the name of Fred that lives in 27540, and it spreads them out as it needs to. With queries, it's the same, but it's a little more interesting with queries because there's also, oftentimes when you're querying, you want to sort as well. And sorting can be interesting in Mongo. It hides it all from you, but let me go through how it actually works. So if you do if the shard key is included in your query, if it's a routed query, basically. So if I'm querying on username, give me all the usernames that start with L. It can ship that off to the MongoDB process that that has that data, that MongoDB process can return them, and it's probably going to have them sorted, maybe not, but it could sort it itself and then return it back as sorted data to the MongoS process, and all the MongoS process has to do is just send it back to you. If it has to do a scatter query, where it has to query all of them, it's a little more interesting, because then it does a scatter gather, or I'm sorry, it does a distributed merge sort in that case to sort them. So basically each shard sorts its subset of data, sends it back to the MongoS process, and the MongoS has to then arrange those in the right order and ship it back to you. And all of that is completely hidden from you as a developer. You just issue the sort command. But it's important to keep that in mind, because there's performance implications. If you are doing a sort on your entire database, that's going to hose your MongoS process. And pretty much any other query that's trying to get in through that MongoS process is going to have a hard time, because it's all hung up sorting all of your data in that one process. So it's important to keep that in mind. Okay, so I mentioned as data comes in, Mongo is splitting chunks and creating all of these chunks. In that example that we had, there were 4 chunks. Chunk splitting happens, well, I really got ahead of myself on those. I kind of went through this whole slide already, too. Chunk splitting happens on the median value. So if we reach that threshold of, what was it, 64 megabytes, I think, or 100,000 documents, if a chunk reaches that threshold, it's going to take the median value, which may not necessarily be the middle. Like in that example I gave before, A through Z, it's not necessarily going to be split on M. It's going to be, if there's more A through F, it might split it on F, so that half are in one and half are in the other. And it's going to create 2 equally sized chunks then at that point.